Hello students, in this video I am going to talk to you about the genesis of the Avogadro number n and why it's a constant. This is actually triggered by one of my students from North America asking me as to why this number is a constant and what is the basis of this number. So I am going to approach this concept from a completely different angle. I am not going to use the usual Avogadro's hypothesis, that is hypothesis that he had postulated. So that I'm not going to use that. I'm going to come to this from a completely different angle. So let's look at it. How am I going to do it? So look, first of all, we have to look at why the gram molar concept arose in chemistry laboratories. See, when you're talking about moles, you're talking in terms of grams, right? Actually moles is related to molecules. So how come it got related to weighable quantities? So see, in the world of practical lab chemistry, it doesn't deal with substances at the molecular level. So when you're going to write the equations, right, 2H plus OH2O, it's easy to write the equation on the piece of paper or the blackboard, but actually when you're doing the actual chemistry in the laboratory, you are going to weigh the substances, right? So you're not going to just, and when you're going to take the substances, you're not going to take one molecule of this and one molecule of that and react them, right? The molecule is so small, right? It's impractical. So you are going to actually react the substances in terms of their actual weight, right? Weighable quantities. So that's why this gram molar concept arose. Okay. So it deals with substances measured in grams and milligrams. Okay. So the thing is, in this video, I'm going to show you how to translate these molecular ratios to actual weighable dimensions like kilograms, grams, milligrams, etc. And in all these dimensions, the units that was chosen by the chemists was grams, for this molar concept. Why? Because this was the predominant unit of measurement in chemistry labs in the 19th and 20th century, and even today. Even though some labs, many labs today, they work in also milligrams and micrograms, and some even in nanograms. Okay, but grams is the standard, right? So that's why the molar mass was also now translated into grams. So how do we do that? Okay, so how do we scale the quantities from the atomic level to gram level? So for example, take a simple hydrogen atom which has got a single proton in its nucleus. So its atomic weight will be 1, right? Because number of neutrons is 0. So 1 plus 0 is 1. So number of protons is 1. So its atomic mass unit, right? That is atomic weight in terms of the AMU is 1. So the next step is to scale from this number from 1 to 1 gram, which will be the gram molar mass of hydrogen, right? So the next question to ask is, how many atoms of hydrogen will collectively weigh total of 1 grams, right? So this was found to be 6.023 into 10 raised to 23. You can do some mathematical calculations, by taking the mass of a proton, dividing 1 gram by that, and you get this number. So this number was designated as capital N. N is also known as the Avogadro number. Okay. So now I will show you how this is a constant, right? So look, when we scale this to other elements, so what would be the gram weight of, say, N or Avogadro number atoms of, say, an element like oxygen, right? So here's where the fact that the atomic mass units scale up in blocks of whole numbers, right? Okay, it's not fractions. Atomic mass units are always whole numbers, right? Number of protons, number of neutrons, that's always been a whole number. And secondly, the mass of each proton and neutron is the same regardless of whichever element you take. Okay, so the proton or neutron in the nucleus of, let's say, beryllium will be the same. Each proton or neutron, the mass, will be the same as some other element, okay, like in oxygen, nitrogen, etc. Okay, so this is what is going to help us now. So now look, oxygen, what is the weight in its atomic mass units? It's got 8 protons and 8 neutrons, so it will be, the atomic weight will be 16 in terms of atomic mass unit. Okay, so each oxygen atom now we can see weighs 16 times as much as a single hydrogen atom. So if we take a collection of Avogadro number of oxygen atoms, its weight will be 16 times as much of similar collection of Avogadro number of hydrogen atoms, right? Okay, so now we have already determined that Avogadro number of hydrogens or N hydrogens will weigh 1 gram. So which means Avogadro number of oxygen atoms will weigh 16 grams. And therefore, and look at 16 is the same numerical value as the atomic mass unit of oxygen. Okay, so similarly, this would be the case with other elements too. N atoms of nitrogen will weigh 14 grams, and 14 is the numerical value of its atomic weight, right, in AMU. If you take N atoms of water, H2O, and that will weigh 18 grams. 18 is the numerical value of its molar mass. So meaning N atoms of any substance will actually be the numerical value in grams of its molar mass in AMU. right? So this is the genesis, and it ties very well with Avogadro's theory that equal moles of substances contain the same number of particles. Thank you and have a nice day. Bye.